Okay, so here's where we were last time. I'm going to go very quickly through the part of this section we talked about last time, just to kind of remind you what we were talking about. It's been a weekend and an exam since we did this. So we are considering scalar line integrals. So in particular, situations where we want to do an integral, something like an integral. We want to take a domain and chop it up into little pieces, accumulate over those little pieces in the usual kind of strategy, but where the domain is dimensionally weird. So in this case, what I've got a picture of is a one-dimensional domain. Let me look at the one-dimensional picture here. Here you go. There's a one-dimensional domain, but it's not on a one-dimensional coordinate system, right? It's not on a single axis. It's a three-dimensional world that this one-dimensional domain lives in. So in that sense, it's a new kind of thing. Nevertheless, it might be, such as in this example here, where I have a metal rod that is sort of bent around in space like that, where the mass per unit length isn't constant. I might still want to compute the mass of it. Okay? So I might still want to chop this up into little pieces like a single variable integral, even though this is no longer, as stated here, a single variable integral. Right? So we have to adapt our idea of what an integral is to account for weird situations like this one. And what we talked about was this construction right here. Namely, it's still the case that I'm adding up the answers to a bunch of smaller questions. In each case, on each little smaller piece, I'm going to be multiplying the size of that piece, which is still length, because it's still a one-dimensional domain. I'm going to be multiplying that by some function for whatever reason. Maybe I'm multiplying mass per unit length times length. Right? Maybe I'm multiplying something else times length because I'm computing an answer to a different application. But for whatever reason, I'm multiplying by some integrand, thus giving me the answer to the question I'm looking for on that smaller piece, and then I want to add up over all the pieces that I've broken the domain up into. Okay, so this is what that definition looks like, and our corresponding notation for that. So this is called a scalar line integral. For the moment, why we go to the trouble of calling this a scalar line integral is not particularly clear. Line integral you can kind of figure because we're doing an integral over a curve, which is not necessarily a line, by the way, so maybe they should call it a curve integral, but they call it a line integral. But why do we go to the trouble of mentioning that this is a scalar line integral? Well, it's because it's going to turn out, and we'll see this later today, that there is a different kind of a situation where I'll want to do something not unlike this, where we're going to be dealing with a very different kind of an integrand. So let me just be vague about that, and I'll get into the details of the specifics when we get to that next kind of integral. Okay. All right. For example, if I want to compute the mass of that rod, well, the total mass is the sum of the little pieces of mass. When you chop it up in little pieces, said differently, mass accumulates, right? And furthermore, on each little piece, mass is mass per unit length times length. Okay. And thus giving me a scalar line integral. Again, this is a shorthand for a Riemann sum argument. It's just easier to write it down with integral notation. Anyway, very common and handy. Okay. All right, and we talked about this other example with the road covered with snow that somebody's going to have to shovel, and computing how much snow is on the road there. Okay. So in terms of how are we going to compute it? Well, if we have some curve in space, and we want to be able to sort of get our hands on doing an integral on this domain, well, it's a weird domain. It's not just that it's bumpy and wiggly, like with change of variables. It's dimensionally problematic, and that really does present a problem. The big picture strategy for how we're going to get our hands on this, or how we got our hands on this last time, is to, just like with change of variables, realize the undesirable domain as the image, by way of some function, of a more desirable domain. Right? Now, when we're doing change of variables, on the right, we had some sort of a bumpy, wiggly domain that was dimensionally convenient, but bumpy, wiggly. And we view that as the image of hopefully a rectangle, or at least a simpler domain on the left. Here, it's just that we have a dimensional problem that we're removing, and we do that by having this function be a parameterization. It's the old idea of a parameterization from way back when. Parameterization means that the curve that you're talking about is the image of this parameterization function that you found. So parameterizations are the perfect tool, and when we take the pullback strategy that we did with change of variables, namely when I take an integral originally written here, and by plugging in from the parameterization, pull everything back and write it all in terms of t's, the result is an integral on an interval on the t-axis. In other words, a Math 111L single variable calculus integral. Okay, so the big picture strategy there is very familiar, and a couple of details to be worked out, namely on a given little piece of the t-axis, and there's a corresponding little piece on the curve, and we need to know our size stretching factor, namely it's certainly not the case that ds and dt are always equal. Of course not. They're very different things. I'm going to need to rewrite ds in terms of dt, and what I expect to happen, and what does happen in most cases, nice parameterization, is that ds is a certain factor times dt. So this size is a factor times that size. Namely, these sizes, this size is a stretched out version of this size. So we call that factor a stretching factor. So we compute that stretching factor directly from the parameterization. Specifically, looking at this picture here, I realize that the size that I'm interested in is the magnitude of that displacement vector, dx. Dx is just the change in the output that results from a dt change in the input. So that dx vector is simply what comes out when you do that little change. I wanted that to look like a vector. That little change in the input. And we have a convenient existing Chapter 4 strategy for how to relate input changes to output changes. That's what the derivative does. Right? In general, it's the derivative transformation, and how that applies in this specific case is some details that are worked out back here. So punchline, really no surprise, is that displacement is velocity times time. Okay, I calculate this with an observation about the derivative transformation, mostly because I want to establish that the derivative transformation will do this for us in general, and this is going to be very, very handy sort of segue into what we're going to do a little bit later today. And we're going to consider sort of a two-dimensional version of this. Yeah, so there's our dx vector. ds is just the magnitude of that. And so here is our handy formula relating ds and dt. ds is magnitude of the velocity vector times dt. And that's the formula that we're going to plug in down here. If you want to compute a line integral, the function, just plug everything in terms of the parameterization. So f is, your integrand depends on position, but position depends on time. So x, y, and z are functions of t, so just plug those in. Nothing really happened in that part. And using the calculation we did on the previous page, length is that. So the size of a little piece of the curve we're interested in is magnitude of the velocity vector, aka speed, times time. So one way to say this is that we found that the magnitude of the velocity vector is our stretching factor, and that's a very reasonable way to think about it. This is really a lot like change of variables in that sense. Sort of an adapted version of change of variables. And this is where we quit last time. Is everybody on board with what we're doing? Any questions? We'll do some examples here in a second. Okay. Right. So notice that everything in this formula, by the way, before I get to the example, everything in this formula over here comes from the parameterization. I get rid of the x's and y's by viewing them as functions of t. That, in other words, by plugging in directly from the parameterization. The stretching factor comes directly from the parameterization. That's the derivative of the parameter, or the magnitude of the derivative of the parameterization. So everything comes from the parameterization. So what you're going to notice as we go through these examples is that the very first thing we're going to do when we're asked to compute, or when we find ourselves needing to compute a scalar line integral, the very first thing we're going to do, parameterize. Because in order to use this formula, we've got to have a parameterization. Right. Okay, so example. So we've got a curved path, which is the top half of the unit circle in R2. And on that curved path, there's a given density function, and it's known that the density is this. So depending on where you are, depending on x, y, and z, the amount of mass per unit length on that curve is this function of x and y. I think I said x, y, and z. Sorry, x and y. It's two-dimensional curve. So what's the mass of the rod? Okay. We've already argued that the way you compute mass, let's observe that mass accumulates. Realize that each little piece of mass is density times length. So that's an old argument from an example that we did previously. So punchline in this specific example, I just want to compute that line integral. And now it's a matter of parameterizing and plugging in. So given, again, note my previous observation, if you want to compute a line integral, first thing you have to do is parameterize. You'll note down here, that's the very next thing that we do. Realizing that we want to compute a line integral, we parameterize. I've got x and y as functions of t. Now, how did I do this parameterization? Well, conveniently, we got lucky. And this curve here, top half of the unit circle in R2 just happens to be easy to parameterize. In fact, we've done this parameterization before. Right? In general, depending on what your curve is, you've got to figure out how to parameterize it. So this is just a nice, easy starting example. Okay. And so what do we do with this parameterization? Well, I'm going to need to plug that in here. My integrand is the density function, and density, you'll notice, is a function of x and y, and so I'm going to have to plug in, for the x and y, I'm going to have to plug in what x and y are as functions of t. So the parameterization is going to go right into there, for one thing. So again, that's just plugging in, nothing particularly interesting there. Where it gets interesting is how the parameterization relates to the stretching factor. Note, I need the magnitude of the velocity, so I'm going to have to take the derivative of the parameterization and then compute the magnitude of that derivative. So there's some details here. Velocity is derivative. So there I'm taking the derivative, and there I have taken the derivative. So that's just calculation. That's taking a couple of derivatives. Don't forget that we need the magnitude of that. And this magnitude is easy to compute. Right? Magnitude's 1, Pythagorean identity. And so very conveniently, our stretching factor is 1 in this case. So all I have to do now is just plug in. It's kind of all over with the shouting. let's see here. So density is a function of x and y, but x and y are functions of t. X is cosine t, y is sine t. Specifically, density was x squared plus 2y squared. Okay, so fine. X squared plus 2y squared. Oh, whoops. Shouldn't have done the 2. So x squared plus 2y squared there. Stretching factor is 1. Don't even have to write that down after that. And now notice I've got an integral. This is a Math 111L integral, and this is something that you guys can all compute. Everybody on board? See how that works? Notice we turned a brand new dimensionally awkward Riemann sum into a good old-fashioned single variable integral. And it's just following the formula. And all of what we've done here, all of the plugging in comes straight out of the parameterization. How are we doing? Right. By the way, if you might perhaps possibly be a little rusty and not be entirely clear on how to do this integral, a lot of y'all might have let some of those chops go over time since you've done single variable calculus. If so, again, now would be a great time. Make sure to brush up and make sure that you're good with all these kinds of integrals. There's nice little tricks involving. In this case, there's a half-angle formula trick that makes this one work out nicely. Okay. All right. Another example. Now, again, I'm going to flash back to a previous application we talked about, namely computing snow on a road. We've already worked out that when you have a road of a certain width and following a certain path with snow depth, a certain function of position, that this is the scalar line integral that's going to compute quantity, volume of snow for us. So I won't go through that again. Just that now I've given us some specifics. The path follows that curve, which you'll note is a graph of a function. And we have this function giving us depth of snow as a function of position. So those things, and one last thing. The road is 3 meters wide. That's going to be the width. The depth of the snow goes there. And we've just got to, parameterize the curve and rewrite everything, plug everything in and rewrite it in terms of t. So in order to do that, I am going to use our good old-fashioned graph parameterization. Everybody remember the graph parameterization from chapter 2? Right? So it's a really nice trick to turn if it should happen to be that the curve in question happens to be a graph, which this one is, and you see it's written, in fact, as a graph, then bam, this parameterizes your curve for you. So that's all I've done there. We know we're going to need our stretching factor at some point, so I'm going to take this and I'm going to have to take its derivative to give me the velocity and work that out, take the magnitude, etc. There's a bunch of details in here. This is just details. I'll let you guys read through the algebra, confirm. Let's observe that we get a kind of an annoyingly ugly resulting expression. But anyway, this is what it is. And so that's our stretching factor. And now it's just a matter of plugging in. Notice that width of 3 just stays there. Height is a function of x, but x is a function of t. So that's what height turns into, is a function of t. Just plugging in for what x and y are. X, in particular, is t. Y is that thing. All right, so just plug it in. And then I just have to insert the stretching factor, this annoying stretching factor that we just computed. And there's your integral. That's a single variable calculus integral, whose computation will give us the answer in question. Now this one is a really annoying one. Gosh, I don't know how tractable that integral is, but certainly this is an integral that represents the answer to our question. And numerically, if we just needed to know, if I needed to be able to, maybe I don't need an exact answer, I just need an answer within the nearest pint, right? Then Simpson's rule, whatever approximation method you might like, would allow you to do that. Okay. So that's it for this section, and now I'm going to go on to a very similar question, which is, instead of what we were dealing with in the last section, was suppose you have a dimensionally awkward integrand in the form of a curve in space. Here now I'm going to ask a kind of analogous question. Suppose you have a dimensionally awkward domain in the form of a surface in space. And for whatever reason, you have some sort of accumulating quantity. So again, what is it we're trying to compute here? Well, there's lots of different applications. I have a favorite sort of foot-in-the-door application, which is mass. Let's suppose I had a surface in space like this, and I want to compute the mass in this surface. Maybe this is a metal sheet that's been bent around in some way, or who knows what. Maybe this is the hull of a boat, and the number of barnacles that accumulate a function of depth in the water, something like that. Who knows what the application might be? But for whatever reason, I have some accumulating quantity over surface. How do I write this down as an integral? Can I do this as a double integral? Not really. Double integrals take place in R2. This is in R3. R3, you say, oh, can I do this as a triple integral? Well, not really. Triple integrals domains have volumes. This doesn't have a volume. It has area, right? So it's got that dimensional awkwardness that line integrals had. So I'm going to have to come up with a new kind of a Riemann sum, but it's so like the other kinds of Riemann sums we come up with. I hope this little process I'm going to go through might even seem automatic to you, maybe even a little boring. And the idea is, well, I have this domain, and I'm going to chop it up into little pieces. And there's going to be a lot of these little pieces. Right? Chop it up into little pieces. On each little piece, argue that what I'm trying to compute on that little piece is easy. Namely, there's going to be an area to that little piece that I'm going to multiply by some integrand for whatever reason. So if I'm computing mass of the sheet, then it would be mass per unit area that I would multiply by that area. If I'm computing barnacles, it would be barnacle population density, right, times that area. That would give you barnacles. And then the idea of this new kind of integral we're trying to define here, this new kind of Riemann sum, I would just want to add up those quantities over all of these pieces. And that is what I have written here. So each little piece of this domain has an area, which I'm going to multiply by an integrand for whatever reason, depends on what you're computing, mass, barnacles, what have you. This product then giving you the quantity you're interested in on each piece. You then add that up over all the pieces. I just have to write this down. Again, it's a very, very familiar idea. I just have to write it down a little bit differently because the details of what are we talking about here are different and new in this situation compared to others. But the concept, the strategy, the same. Okay. So, again, I'm going to write down a new notation. This is the notation we use. You'll notice that we use the two integral symbols because this is a two-dimensional domain. that we're interested in. So we're, in some sense, it's sort of a two-dimensional accumulation. Size is area, right? And other than that, I think the notation is pretty familiar, pretty natural. Okay, so a quick example. Again, we've kind of talked our way through this, but if you have a curved sheet of metal, and if the mass per unit area is some function of position, well, the total mass is the sum of all the little pieces of mass you might chop it up into. And on each little piece, mass on such a little piece is mass per unit area times area. So again, I haven't really, I haven't gotten an answer. This is not an answer to our question. This is just a notation representing the strategy for how we're going to go about getting our answer. Nevertheless, it's progress. Okay, let me pause on that for a second. Does anyone have any questions? I think I see the analogy between this and scalar line integrals that we just finished talking about. It's, again, very, very similar. The strategy for computation is very different, but the Riemann sum construction is not that different. Right, so let's worry about that computation. And keep in mind we're going to be looking at one little piece of area at a time. That piece of area that we're interested in is something like this, and I need to know the area of that. How we're going to get our hands on that? Well, no surprise. Find myself looking at a domain that's awkward for whatever reason. With change of variables, it was because it had corners and curves and stuff like that that made it awkward and undesirable. With scalar line integrals, it was the dimensional awkwardness and maybe also the curviness. Here, again, dimensional awkwardness. Right? It's a two-dimensional thing in a three-dimensional world. It's not a double integral. It's not a triple integral. It's this weird kind of different kind of thing. How do we deal with awkwardness? How do we deal with undesirable domains? We view them as images of more desirable domains. In this case, we parametrize, just like with line integrals. And viewing, as we have now, our undesirable domain as the image of a more desirable domain, we just have to talk about the details of the pullback. And the pullback is, again, going to be kind of familiar. All the stuff that's over here, we're just going to rewrite it all in terms of these new variables, u and v, in the domain of the parameterization. Okay. And again, the stretching factor is the one thing that isn't just a direct plug-in. So I've got to figure out now, if I break our new domain up into little sub-rectangles like that, and if it has as its image some little shape like that, it's going to be, I appeal to your geometric intuition, this rectangle through the parameterization is going to give you a distorted rectangle over here. And a rectangle, when you distort it, it's going to give you some sort of oriented parallelogram-ish, something approximately parallel. And I want to know the ratio of the areas. Namely, what I really need to know is this area of that thing, but I want to rewrite it in terms of this area of that thing. I want to know this in terms of that, and the relationship is going to be that this ds area is some scalar multiple of this dA area. Namely, there's going to be a stretching factor, an area stretching factor. Okay. And I'm going to get at that by computing ds. And it's going to happen to turn out that it'll end up being a multiple of dA. Okay, so how do I compute ds? Well, let's again sort of look at, I'm going to zoom in now on each of these little small pieces. Here are those zoom ins. oh, sorry. Here's the, well, okay, let's click good enough. So how am I going to relate this area to that area? So I've got the parameterization, but it's not clear how I'm going to use the parameterization to relate area, input area to output area. What I know how to do with functions is relate input changes to output changes. That's what the derivative will do for me. Right? So I don't really know how to plug in an area into a function and get an area out. So what I'm going to do is realize then that I have to take this sort of one little step at a time. I have to plug in and ask, okay, if I look at that change there, that little vector representing a change in the input, what is the corresponding change in the output? And then likewise, what about this change in the input? And it's going to have a corresponding change in the output. That I can do with derivatives. The derivative transformation is the perfect tool for that. Input changes relate to output changes. And then I realized that, oh, well, these two input vectors define my input area, dA. Right? These two edge vectors, these are the edge vectors of a rectangle that clearly has area du dv. The output vectors are the edge vectors of the parallelogram whose area that I'm interested in. Right? And so, and side note, chapter 1 tells me how to compute the area, this ds area of a parallelogram when I know the edge vectors. There's a handy-dandy chapter 1 formula for that. Magnitude of the cross product. So I'm just going to compute these two vectors, plug them into that chapter 1 formula for area, and that'll compute ds for me. Computing those two vectors, hopefully this will look familiar. I put in these two input vectors, apply the derivative transformation. Apply the derivative. That's the derivative transformation of this function, this parameterization function. These two input vectors, when I apply the derivative transformation, compute, and I'm going to get these two output vectors. Everybody happy? Now, the details of this calculation, no big deal. They're actually a lot like what we did with line integrals. Namely, I'm applying a derivative transformation to a vector. Scalar factors out. This I recognize as a partial derivative. And I'm done. It's using old facts from chapter 4. Does everybody follow that? Likewise for the second vector. Now, I'm not going to go through this because you can see how very, very similar that calculation is. It's just that now it's the second standard basis vector, and so you get a partial with respect to the second variable. Okay. So altogether then, these two vectors, xu du, xv dv, are the two edge vectors of the parallelogram. So there they are, xu du, xv dv. Their cross product, I need to get this all on one page. Their cross product is the vector whose length gives me the area. Cool? So, and then here it is. These are the two edge vectors that we computed. Oh, again with the zooming wrong. These are the two, what color did I use? blue. Okay. These are the two edge vectors that we computed from the derivative transformation. We take their cross product, and the magnitude of that cross product is the area we're looking for, ds. And then we just simplify, again, nice properties of the cross product. These scalars factor out. All right. Then you're left with just xu cross xv. And notice that du dv is dA, and so we have a relationship between ds and dA, and that relationship, here you go, there's your stretching factor. Your stretching factor is the magnitude of xu cross xv. Okay. It's a formula to remember. We've done this computation, and then henceforth we can use this anytime we need it. Okay, is that pretty good? A couple of details to this. I mean, it works out a little bit differently than it did for line integrals. It was the magnitude of the velocity vector. Here, it's the magnitude of, the little bit more difficult formula, but it's just something that comes out of looking at the derivatives of the parameterization. All right. And that gives us our formula. If you want to compute a scalar surface integral for whatever reason, again, why would you want to? Why are you computing a scalar surface integral? You've got some sort of a surface. Something is accumulating on that surface, whatever it might happen to be. Something per unit area is getting multiplied by area. And the way you compute that integral, that scalar surface integral, is to realize that your integrand as a function of position can be rewritten in terms of u and v, so go ahead and do that. That's just plugging in. Nothing really happened there. Area is a stretched out version of area in the uv plane. The stretching factor, I have a formula for it. Side note, it does end up being convenient to refer to this xu cross xv as capital N. It's just a notational convenience. We're going to be using this notation throughout the rest of the book, by the way. So go ahead and make a mental note that capital N here on out is going to refer to xu cross xv. Okay, so we have a plug and chug formula. Any questions? Okay, let's plug and chug a little bit. Look at an application. Again, we've already sort of worked through the first half of this application. We're going to compute a mass of a surface. We have a metal sheet. It's in a certain shape, graph of a certain function, over a certain region of the xy plane. So we have a surface, and I'm given that density is given by z squared, and I want to compute the total mass. Okay. So, sequence of observations. First, we observe that mass accumulates. Total mass on this surface is the sum of the little masses when you chop it up. So, immediately. On each little piece, again, we've already talked about this. Mass is mass per unit area times area. Okay. So, here's that double integral we want to compute. And in order to compute, notice that our formula for computing involves the parameterization. Everything is written in terms of the parameterization. We're going to rewrite the integrand in terms of the parameterization. The stretching factor is computed from the parameterization. So you've got to have a parameterization to use this formula. Everything here is done from the parameterization. So step one, we've got to parameterize. And you'll notice that, again, because I'm looking at a graph, I've used the graph parameterization. All right, so again, this is a trick from Chapter 2. By the way, this is, you might have noticed we've done a lot of parametrizing in the last couple of sections here, and we're going to be doing more parametrizing. It comes up a lot here at the end of Chapter 5 and a lot in Chapter 6. So this would be a great time to go back to Chapter 2 and review those parameterization methods. The graph parameterization being the big one. Right? This is the one that gets used really often. And then variations of it and other tricks, of course. Okay, so you'll notice in here, a quick observation then, the function whose graph you're parametrizing shows up there. Okay. Right, so we've got a parameterization, and we're going to need to know our stretching factor. Keep in mind our stretching factor is computed with that formula. This is the definition of capital N. So I just need to compute XU cross XV. I'm going to do this one little step at a time. First, I'm going to compute XU. XU means you're taking the U partials of your parameterization. Those partials, not that hard to compute, right? But something that's got to be written down. XV is the V partials of that exact same parameterization, of course. Again, there's 3 partials you have to compute. Go through one at a time. There they are. Now, I've got to compute a cross product. Go back to Chapter 1. Remind yourselves, make sure you remember how to do cross products. So, working that cross product out in this case, you get that. And lastly, make sure to remember that what we're interested in here is the magnitude of that cross product. So you've got to compute that magnitude, and that gives you that. There's a certain amount of tedium that goes into this, but this is how that stretching factor is computed. Everybody follow the details here? Any questions? So with that stretching factor computed, it's all over but the plugging in. So note that density is a function of position, and now position is a function of the parameter variables. So that's just plugging in. ds, stretching factor times dA. And that stretching factor we just computed here. And again, now we've got it down to a single variable. Oh, excuse me. Now we've got it down to a more familiar integral. So this is a double integral in R2, but nevertheless, not that bad. By the way, any instincts on how to compute this double integral? It actually kind of does look sort of bad if you really think about it. Anybody have any knee-jerk reactions to what might be a good method for this? By the way, what is this computed over? This is computed on this domain D, which is the unit disk in the xy plane. Well, the uv plane, because x and y are u and v. So the unit disk in the uv plane is our domain. You look at this integral, polar coordinates. Right? Use polar coordinates to make disks into effectively rectangles, which are awesome. And it makes these kinds of functions a lot simpler. So this integral would be perfectly doable. Well, still inconvenient, right? But perfectly doable if you switch to polar coordinates. Everybody happy? All right. So one more example. This is kind of a weird example, but I think it's fun. So the hypothetical here is that we're at an aquarium, and they have these enormous tanks at the aquarium. How many of y'all have been to like real aquariums? You know, where they have like okay, quite a few. If you haven't been to one of these things, they have these enormous tanks under 20, 30, 40 feet of water. I mean, just gigantic. And then these huge sheets of plexiglass that make up entire walls of these things, and you can look through and watch. It's really very cool. So I'm visualizing a variation of that idea. One of the problems that comes up when you're at an aquarium is that if you're looking straight through, perpendicularly through the glass, then you get a relatively undistorted picture. But if you look off angle, then everything's distorted and weird because of the index of refraction of the glass and the water, and it's strange looking. So my idea is, suppose that here's your water, the top of the water, and throw all this water down here. And the idea would be that there would be a glass dome, hemispherical glass dome, such that if you put your head right here, then as you look, because your head is right at the center of this dome, everywhere you look, right, your line of sight is looking perpendicularly to the glass. So I don't know exactly how this would work out. There might be some magnification issues, but this would be an interesting solution to the distortion problem. Now, in order for this to be possible, of course, there'd have to be some sort of a hallway underneath the water, so that you can walk around. Oops. So that you can walk around underneath and put your head in just that right spot. So if this is going to happen, if we're going to make such a thing, then we need to know how much force is on this dome, and that's what the purpose of this question is to compute how much grand total force is there. I don't need him anymore. How much force is there on this dome? Okay. Now, force is pressure times area. So those of you who have had intro physics courses, force is pressure times area. Pressure depends on depth. So it'd be tempting to say, well, let's just take the depth of the water and multiply by the area of the dome, and there'd be some constant thrown in, and that would give us the total force. But the problem is that different parts of this dome are at different depths. Over here, the depth is smaller. Over here, the depth is larger. Right? So again, non-constant depth, and so we have this situation where we can't just compute directly. What I can do, though, is argue that I could break the dome up into little pieces. On each little piece, the depth is approximately constant. So on that little piece, I could compute the pressure as a function of depth, multiply by the area, and that would give me the force on that little piece. And then I'd want to add up over all of the little pieces of the dome. Namely, it's a double integral. A surface integral, one of these scalar surface integrals. Okay, so here's that process. Now I'm going to let you guys walk yourself through the Riemann sum details. This is what it turns out to be. The punchline is that this is depth, which relates to pressure. That's what's getting multiplied by area, and pressure times area gives me force, and force accumulates over the entire surface. So that part of the problem is just a sort of a direct, rewrite what we're interested in terms of what we have. So now, in order to compute this double integral, I've got to parametrize. Look back at our object. We need to parametrize that surface. That's a sphere centered at the origin. And that's not that hard to parametrize, right? You can use spherical coordinates in particular. So the spherical graph parameterization, noting that rho is equal to 1. Is how we write that in spherical coordinates. And with rho equal to 1, I get this parameterization. Are you on board? Okay. So we have a double integral, we have a parameterization. Now it's just a matter of doing the pullback. All the stuff here is written in terms of x's, y's, and z's and all that. This is the parameterization through which we do a pullback. We're going to now rewrite everything in terms of phi and theta. By the way, notice we're not using u's and v's, we're using phis and thetas. It doesn't really matter what your parameter variables are here. Effectively, phi and theta are going to play the role of u and v from the previous examples. And yeah, so there's some details here. Again, you've got to compute your stretching factor. This is something that everyone should go through at least once in their lives. It's not that bad. So I encourage you to follow through the details. I'm going to leave this for you to do. Notice, though, I'm just computing the partials. And then doing the cross product. And then computing the magnitude of that result. Structurally, it's the same calculation that we did in the last example, just specific to this one. And when you're computing this magnitude, it's really interesting how Pythagorean identities come up several times, and the punchline is that the whole thing simplifies to sine phi. It's kind of awesome. So that's why I say everyone should go through this once in their lives, just to see how that algebra works out and everything comes down to be this simple. So walk yourself through those details. But punchline is that is our stretching factor, sine phi. So that goes right there. Stretching factor is sine phi. That's what allows you to rewrite ds, the area of a little piece of the dome, in terms of d phi and d theta. Everything else is just a matter of plugging in. And now you have a double integral, and this is again a perfectly doable double integral here. Again, you're going to have to remind yourself of certain trig integrals and certain tricks that you can do for, but these are easy, and make sure that you can do that. Make sure you can work out that double. All right, how we doing? Everybody happy? All right. So I think it'd be a good idea to do the following. This would be a nice exercise in seeing connections between different ideas that we've talked about. So we just talked about scalar surface integrals, and there was this little process where we computed the stretching factor. Previous to that, there were scalar line integrals. We went through a little process where we computed the stretching factor. Then before that was change of variables. We went through a little process to compute a stretching factor. In all three of those examples, and it's taken us several days to get through that, so, anyway, I'm making references to things we did several days ago. But I want you to go back through and look at those stretching factor computations and note that in all three examples, we had an input and an output. We wanted to relate input size to output size. We realized that means I had to look at certain key input vectors and look at their corresponding key output vectors. And input vectors and output vectors were related by the derivative transformation. So all three, these very different contexts, scalar line integrals, scalar surface integrals, change of variables, 2 dimensions, 3 dimensions, arguably 4 different contexts. And in all cases, the derivative transformation is what was the sort of the foot in the door to relate input size to output size. And the only thing that makes these examples different is that the context, the geometry of the specifics of the context in question were just different in those 4 cases, and so you get a different little formula at the end. Sure, maybe you're using a determinant, maybe you're using a cross product, maybe various different things, but that's just because of the context. Right? Really, all 4 of those calculations are extremely similar. So I think it's a lot of value in looking back through and seeing those similarities. And whatever you understand about any one of those, you can use to help yourself understand the others. And it's a valuable little exercise, so I encourage you to do that. Okay, lots of exercises for you to work through. So, new topic now. I'm going to talk about a new kind of an object. something called a vector field. This is going to end up being extremely important in Chapter 6. One of our primary objects of study in Chapter 6. So the purpose of this section is just to tell you what they are and why we're interested in them. What do these things represent and how do we write them down algebraically. So in particular, we're going to be looking at a new kind of a function. Instead of looking at scalar functions, so these are functions where the value of the function is a scalar. And let me observe that all of the integrals that we've done so far, let's talk about what was the integrand. Density, population density, width of a road times depth or something, right? And various different quantities that we've had be our integrands, they're all scalars. They're all numbers. That related to various different applications for various different reasons. A lot of variety, but ultimately all numbers, scalars. We're going to consider now a new kind of an object. It's eventually going to be an integrand, eventually. We'll get to that, how that works out later. But the value of these functions are not going to be scalars. They're going to be vectors. So these are vector-valued functions. But they're vector-valued functions that we think of in a specific way. So I'm going to lead into this with just a bunch of examples. So I want to talk about something called a force field. We call it forces are represented by vectors. Right? Forces have, so this remote control is applying a force to my hand. That means two things. It means that there's a magnitude, namely what's the weight of this remote control, but there's also a direction. Right? This remote control is not applying a force that way to my hand. It's critically applying a force that way to my hand. So magnitude and direction. So a force field is a very closely related idea, and it's just an observation that sometimes you have forces, namely vectors, associated to particular points. So, for example, here is a very rough picture of the force field created by the Earth's gravity. This is what we call a gravitational field. You could say a gravitational force field, but people typically just say gravitational field. In particular, note that at every point there is a corresponding vector, namely the amount of force of gravity experienced at that point, assuming that you have a given amount of mass. So that's a vector field. For every point, there's a corresponding vector. Here's a different point, different vector, different direction, different magnitude. Right? Here's another point. Again, different vector. All right. So this is all a vector field is, for purposes of Math 212, is something that associates to every point a corresponding vector. And I think the gravitational field is the most sort of intuitive, well, it's one of the most intuitive and relatable such examples. Let me pause on this for a moment. How many of y'all have seen in a physics class something called the electric field? Show of hands. A few of you. Okay. Well, it's not that. It's morally actually pretty similar. You think about it. An electric field, you have certain charged particles distributed however they might happen to be distributed, and wherever you are, there's going to be an electric field vector. There's going to be a certain amount of electric repulsion or attraction at that point, depending on how other charges are distributed. Okay, so we call it a force field here because here the vector in question that you associate to a particular point, that vector represents a force. In this case, that's the name force field. Okay, so there are other kinds of vector fields. I like to call these flow fields. Again, there is going to be a vector that you associate to a particular point, and it's just that now we're not going to be interested in forces. sources. There's no forces involved here. But if you have a fluid flowing around, such as, let's say, in this room, right, there's air coming out of air vents, and I'm talking, and that's blowing a certain amount of air, and who knows what else is, but there's a flow of air in this room. So at any particular point, let's say here, you look at that point, let's say the wind is going that way, right? Then at that point there is a vector that represents, let's say, the velocity of the airflow at that particular point. So for every point, there's a corresponding vector. Again, vector field. So here's a picture of this kind of thing. Suppose I have water moving in a river, or across the concrete after a rain, something like that. At any given location, there's a corresponding velocity of the water at that point. Let's say that this is a river. You'll notice that over here near the bank, at that point, there's a different velocity vector. In this case, a shorter velocity vector, so a smaller, because the water doesn't move as fast near the bank as it does in the middle. Okay? So for every point, there's a corresponding vector. Again, in terms of the physical interpretation, this is a very different kind of a thing. This is not representing forces. Not interested in forces here. Here we're not representing forces as a function of position. Here we're representing fluid flows, fluid velocities as a function of position. Instead of a river, here's a different fluid flow. Here's, I'm looking from above. Let's say I'm painting a room in my house, and I'm looking from above at a can of paint that I have stirred. Right? And if you stir it, well, then wherever you might happen to look, there is a corresponding velocity of the paint. Right? At the middle, there's no velocity. It's not moving. It's flowing around that center point. Right? So different points, different velocities. Does that make sense? Everybody happy? So, side note, both of these examples are very, very important. Both of these, so force vector fields, and flow vector fields, such as this one, aka flow fields, are going to be really, really important when we get to Chapter 6. I mean, some of the objects that we're going to be computing in Chapter 6 are very naturally thought of as relating either to forces in a vector field or flows in a vector field. They're so natural that even the terminology that we use to describe certain of these things depend on these physical interpretations. So these are the two most important physical examples of force fields that we're going to see in this course anyway, and probably in other situations that you'll see these things. So make sure to spend some time thinking about, how is it that in this case, for example, how is it that this vector field is representing the flow of paint in a paint can, right? Or the flow of water in a river, versus how in this example is a vector field, mathematically identical for every point of this corresponding vector, representing a very different physical object, namely the gravitational force in this case at points nearby mass. Okay, so it's good to chew on and distinguish these examples in your mind and realize how both of these very physically different examples are all represented by the same little mathematical object, namely that at every point there is a corresponding vector. Okay, so a vector field we call it. All right, one last example. I'm going to make the observation that if you have a real valued function, there's one. It's a familiar function. We've done a lot with this function over the first several chapters of this book. Real valued, you'll notice the values of this function are real numbers. One of the things that we've done with a function like this is to compute the gradient vector. Here's the gradient vector. And the gradient vector, we've thought of this in different situations. Mostly we've thought of this as, suppose you're at a particular point, we've fixed a point, and then talked about what you can do with the gradient vector at that point. Namely, it points uphill, direction of fastest increase, its magnitude is useful, etc. Okay. But notice also that this is actually a vector field, because at every point, x comma y, there is a corresponding vector given at that point. And that's what a vector field is. Now, we might have thought of this only one point at a time. This is the point we're actually interested in, and given that we're here, and given other things that all have to do with that point, we had this one gradient vector that was helping us compute various different things. But I could instead say, well, yeah, but at that point, that's the gradient vector, and at this point, that's the gradient vector. So, in fact, this thing here is a vector field. So I just thought it was an interesting thing to point out, but not so. In fact, even though we didn't think of it that way at the time, and we certainly didn't really think about this picture, nevertheless, in fact, we have already seen some vector fields. Namely, every time you've written down a gradient and thought of gradient as a function of position. Side note. Oh, yeah, question, go ahead.
How are the functions for vector fields
written down? Yeah, totally. That's the next thing we're going to talk about. It's a great question. Just give me 2 seconds. Yeah, right. One last observation I want to make about gradient fields in particular. So when you have a real valued function, you compute its gradient, and you can interpret that gradient as giving a vector associated to every location. Turns out, for reasons that are extremely not obvious right now, gradient fields are particularly important in Chapter 6. It's going to turn out that gradient fields have special properties that other vector fields don't have. And furthermore, gradient fields are the answer to some extremely natural questions that we're going to want to ask in Chapter 6. So this is just a little bit of foreshadowing, but another reason why I wanted to show you this example is that these are going to be really important in Chapter 6. Okay, so let's talk about how do you write these things down mathematically. The definition is that a vector field is a function from Rn to Rn. Turns out that this is exactly how, in fact, you represent such a thing. Now, here's the picture. So, for any given point in R2, for this picture at least, so notice my input point, what I'm calling my input point for this function. I'm picking a point in R2. And at that point, I need to tell you the corresponding output vector. Well, that output vector is a vector in R2. Right, so it's something that does this. If you have some way of associating to every point an associated vector, then what you have is a way of associating to every element of R2, thought of as input points, thought of as input points to some function. You get a corresponding vector in R2, thought of not as a point, but thought of as a vector. So it's actually a pretty natural way to write such a thing down mathematically. It's just a function from Rn to Rn. And I'm going to give you some examples in a couple seconds. The first thing I want to do is point out how we're not thinking of vector fields. Don't think of one of these functions, from R2 to R2 in this case. Don't think of this as having input points and output points. A domain over here and a target over there. Now, this is a great way to think about some functions in some cases. For example, this is how we would think about a change of variables function. And we have, right? We've thought of output x's and y's as being functions of input u's and v's, and pullbacks and all that kind of stuff. We did a lot of good stuff thinking about these kinds of functions in this way. But vector fields, even though technically a vector field is a function from Rn to Rn, just like a change of variables function is, we're critically thinking of a vector field in this different way. And if you're counting, I think this is geometric construction number 5 for how we think about functions in this class. So let's count them up real quick. You can draw the domain and target separately, like I've done here for change of variables functions. Thinking about derivatives as relating input changes and output changes. We've done a lot of good stuff thinking about the domain and the target separately. You can draw graphs. That's the second picture. You can talk about level sets in the domain. That's the third picture. You can parametrize, which means you're looking only at the image in the target. That's the fourth picture that we talked about. And now we've got this fifth picture, arguably pretty weird, but where you think of both the input and the output in the same space. You just think of the input as a location and the output as a vector associated to that location. It's just a different kind of a picture. So it's not a graph. It's not a level set. It's just a different kind of a picture. Everybody happy? Okay. Right, so a couple of examples. Let's look at this. So I claim that's a vector field. Notice that for every input point, x comma y, for every input point, there is an associated vector, and the vector is 2, 1. So at every point, I draw the vector 2, 1. And notice that's the same vector for all points. It doesn't even change depending on x and y, so that's a pretty easy to draw vector field. Always the vector 2, 1 for every point. Yes? Everybody good? Yes.
Could those possibly ever be in like different directions, or is it literally always going to be like?
Oh no. This is the world's simplest, easiest example. Just to get our feet wet. I was just pointing out that just for starters. Yeah, no, it's usually not this easy.
It's at sort of like lengths, I guess, of the vector. Just
No, it's spitting out vectors. Right? I mean, what comes out of this function is this vector. It's just not a real valued function. It's a vector valued function. So yeah, so the outputs, again, drawn as vectors associated to the input points. These vectors. Okay. So let's see another example. Here's one. F of xy equals xy. Now this is a kind of a weird vector field in that given an input point, the vector that I associate to that point is in fact exactly the position vector for the original input point. So that has a picture that looks kind of like this. So for any, which colors did I use here? Okay. So for a given input point, let's say that one, to that vector, to that point, I associate the vector with the same coordinates. So if you were to think about this green point here as it's got an x and a y coordinate, if you were to take that and view that as a vector that you put at that point, with its tail at that point, then you get that blue vector. And if you do that for sort of every, I've done this in this picture for a sampling of points in the xy plane. Every point, there's a corresponding vector. In some sense, it's radial. It's always pointing radially away from the origin, with the magnitude increasing as you get further away. That's kind of a weird vector field. Here's another one. You can plot a few points here, namely plug in some x's and y's, get your associated vectors, start assembling a picture one point at a time. It's very convenient, though, to make a couple of geometric observations. That is to notice that the input point and the output vector are nicely related. And you can see this straight from the formula here. Notice they have the same magnitude. Input point, output vector, square root of x squared plus y squared in both cases. So they have the same magnitude, and furthermore, their dot product is 0. So that means that this point thought of as a vector, the associated field vector for that point, always orthogonal. And so that gives you this picture. So the point thought of as a vector, and then the associated field vector, same magnitude, orthogonal directions, and you get a picture that looks like this. Does that make sense to everybody? Okay, so that makes a great stopping point. So we're done with 5.10 now, and we will pick up with 5.11 next time. See you guys later.